being handled here. For example, you see you have the image being captured like this. So now you have the almost half of the face data present in this example. So whatever pose you want to generate, you can actually rotate this and then get that pose information from this sample. So very easily we can handle the pose. There are some advantages we have with the 3D data, and that is why we are basically uh, trying to explore how to use 3D data when we are using deep learning. Okay. There's another a good thing about the 3D data that we see here. So sometimes we find that the 3D data, sometimes 3D data is used alone, but many times we find that the sensors that we are using for capturing the 3D data, they can also capture the 2D data. So if we have this a sensor which can give you the 2D image and corresponding 3D image, then it is going to be even more helpful in performing different tasks, because you will be having 2D in 2D representation, and along with that you will be having exact same thing represented in 3D. So you can make use of actually both, and then you can have a system which is a kind of multi-model system, and then you can have even improved performance for your different tasks. Okay, so 3D data can be actually covered with 2D images if they are registered with each other, and then we can make use of that. So that's another good thing about 3D data, because 3D data and 2D data both can be used, and uh, better performance can be achieved. Now let us see some broad applications where the 3D data is being used. So some of the applications I've written here. For example, in the robotics, when the robot is navigating, it captures the world around it using 3D sensors, and then analyzes it to take the decision. In augmented reality, we have the huge use of 3D data. Similarly, in autonomous driving, there also again you have sensors which are capturing the world around it using 3D sensors, and then uh, the the movement of the car is decided based on the the captured 3D data. So this is another area where 3D data is heavily used nowadays. There's another domain where we have the existence of the 3D data, but this data is a bit different from the kind of 3D data that you have in these three cases, right? So the area I'm talking about is the medical image processing. So I'm sure many of you must be aware of this fact that in the when you are dealing with the medical data, it's like MRI data, the CT scan data. This data actually represents the volume. So always whenever you have any MRI, let's say image, it is a collection of many scans, right? So and which are if you stack them together, that creates a volume. So here also, in case of medical image processing, you have the representation of 3D data. I mean, you have the representation of the object in terms of 3D data, but remember here, this representation is uh, different from the other three representation that I'm talking about here. And what way it is different?
Hello, sir. Dear participants, sorry for the issues. We'll be dealing with it. We'll rectify it soon. Thank you.
Yeah, I'm extremely sorry. I hope I am audible now.
Yes, sir. Yes, sir.
Okay, sir.
Thank you. So I was just explaining to you broad applications of 3D data, and I just mentioned that there are very variety of fields where it is used, and one of them is the robotics. Another one is the augmented reality, and then you have autonomous driving, and then there's another field I was just explaining that that is there. It's called it's the domain of medical image processing, where you have the 3D data, but this 3D data is different from the 3D data that we have in these previous three examples. And the main difference comes from the fact that in other three cases, we are actually representing only the outer surface of the object. But here, when you are representing anything in medical image domain, this is actually the information of the complete volume, right? So along with the outer geometry, you are also representing its interior, and that's where you're getting the complete volume being represented. Okay? There are a few tasks where the 3D data is used, like object classification. So they were in the previous slide I have shown you the different application areas, and then in these application areas, you see you perform different types of tasks. For example, object classification, object recognition, object part segmentation, semantic scene parsing. These are different tasks that actually perform in different areas when you are dealing with the 3D data. So let us move forward. So we see that if you just analyze the timeline and the use of the 3D data, we find that the use of the 3D data has actually started, and particularly the use of deep learning on 3D data, it has started after 2015, because we see that after 2015 there were some public repositories where the good amount of 3D data was available and so on. But if you see the time before that, like around 2010, if you see the existence of the 3D data, or if you go through the papers that were published around 2010, you find that all of them were actually using these two 3D samples. One was the Stanford Bunny, and then another was the Utah T-Post. Because so they all were actually forced to use only these two samples, because no other publicly available database or any public samples were available. Okay, but during that time, if you see, or maybe before that, you have good amount of public repositories where we were having 2D samples, 2D images. For example, you see one very popular database that was used during that time was the Princeton Safe Benchmark. So since most of the data repositories were actually dealing with the 2D images, so we see that there was not much work done prior to 2015 in the domain of 3D data, and particularly the use of 3D data in the deep learning. Later, we see that there were many ways that the 3D data was created, and that actually led to the use of 3D data in the domain of object recognition and different tasks, and the use of deep learning in processing the 3D data. Okay, so, like nowadays, we see that there are a lot of online repositories where actually you can get the 3D data. Similarly, there are many crowdsourcing platform where you can create the 3D data. For example, some of them I mentioned here, and also now the main 3D data is generated with the help of sensors. So now we see that there are a lot of very cheap sensors available with the help of which we can create the 3D data. One of the popular 3D sensors, I'm sure many of you must be aware of, is the Kinect sensor. It's very quite cheap, and then it generates good quality data in 3D. So because of all these reasons, a lot of public repositories are there, and then a lot of 3D samples exist, and due to that, now we see that good amount of work being done in the domain of 3D, and the deep learning is being used here. Okay. So as I said, the work in the domain of 3D deep learning started around 2015, because these two popular data sets were available that time, ModelNet and the ShapeNet, and people were using that for analyzing their models and then their proposed techniques. Okay, so because of because of this, one of the reasons the 3D deep learning started, that was because of the surge of the 3D publicly available 3D databases, and another was there was also a huge demand from the industry was coming, because as I showed you, there are many applications like robotics, autonomous driving, virtual or augmented reality, smart manufacturing. There are many places where the people are actually looking for the use of 3D data and then performing different applications. And because of all that, now we see the good amount of work being done in the domain of 3D. Now let us move forward and then discuss. So we have completed the first part of the first part of this talk. Now let us move to the second part, and here we'll understand what are different different types of tasks that we perform when we are using 3D data. So all the tasks that we do with the help of 3D data, we can actually categorize them in these three broad categories. One is the 3D geometry analysis, another is 3D synthesis, and then the last one is the 3D assisted image analysis. So let us quickly see them one by one, very briefly. So in case of 3D geometry analysis, you have the presentation, you are having the representation of the object in 3D, and then you are making use of that to perform these different tasks. So you can see here, basically you are analyzing the geometry and then making use of the information that you get from this analysis to perform different tasks. In case of 3D synthesis, as the name suggests, you are basically synthesizing 3D data. So here your input could be the 2D images, and then you are synthesizing the 3D data, as you see in this example. Or sometimes you may be having a case where you have object being represented in 3D, but that object is not completely represented. Let's say some parts are missing, or some parts while scanning, some parts of the objects were hidden, and that's why the camera could not capture them. So you may be completing that missing thing. This is a very common problem is called safe completion of the 3D data, so or 3D object. So here also again you are generating the 3D data. In the first example here, in the first case, you are generating the 3D data from the 2D samples. Now here in the second case, in second example, you have 3D data, but some parts are missing, and then you are completing those missing parts. So here also you are synthesizing and you are generating the 3D data. And sometimes you might be also performing 3D modeling and shape modeling and then generating the 3D data. In the third case, which is 3D assisted image analysis, here, as the name suggests, it says you are doing the image analysis where the 3D thing is assisting you. So, for example, you might be performing the 2D. You might be performing, let's say, the content-based image retrieval, where you are searching for a given input image. You are searching similar images in your database, right? And the query is also represented in 2D, and the result and the database is also represented in 2D. So when you are searching, one option is that you can only make use of the 2D information that you have, and the another information is that you can make use of the corresponding 3D information that is available for the 2D object, and then with the help of that you refine your objects, refine your results. So here, in this case, 3D, the input and output both are in terms of 2D images, but in between, during the processing, you are making use of the 3D data to perform your task more efficiently. Okay? So just to summarize, in case of 3D geometry analysis, and this all we are talking in reference to the deep neural network, so that is why you see the deep neural network is here. So here, in case of 3D geometry analysis, the input is going to be 3D, and then based on that you are going to analyze and then produce the output. In case of 3D synthesis, the input is going to be 2D image, and with the help of that you are going to get the or going to generate the 3D data. And in case of 3D assisted image analysis, as you see, input and output both are in 2D, but in between you are making use of 3D to refine your results, to perform your task more efficiently. Okay? So this was a brief overview of different types of things that you can do with the help of 3D data. Now, if you see these two tasks, 3D geometry analysis and 3D synthesis, in that in these two tasks, you see that in real sense you are making use of the 3D data, but in the third case, which was 3D assisted image analysis, your input and output both were in the domain of 2D. Only during the processing you are making use of the 3D data. Okay. Now let us move forward and then discuss the main part of this session, which is use of deep learning in the case when you have data being represented in 3D. So to understand that, let us first see different ways that we use to represent the 3D, represent the 3D objects in 3D. Okay? So before we move forward to discuss the 3D representations and their issues, let's first see in what way you are representing the images in 2D. So you must be aware of this fact that whenever you have an image, it is represented in computer, and I'm talking about the 2D image, as you see here, the 2D image. When you have a 2D image in computer, it is represented in terms of a matrix like this, right? So if you have, let's say, 100 cross 100 image in the computer, you are going to store that 100 cross 100 image in terms of a 100 cross 100 matrix. Okay. If it is a color image, then it is going to be, for the grayscale image, as you see here, it is going to be a 2D matrix. But if it is a color image, then you're going to have a 3D image. Okay. Sorry, 3D matrix. But this image in computer is being represented in terms of either 2D matrix or the 3D matrix. And one important point that you can note down from here is that when you are representing or when you are storing your images in computer, you have this unique way of representing the image, right? Whenever you are representing the images, you are going to represent them in terms of these 2D or 3D matrices. Okay, but that is actually not true with the case of 3D representations. You have many ways of representing the objects in 3D or in terms of 3D data. Okay, and that actually creates a challenge. So we'll see here. We are saying that there's only unique way of representing the images in computer, and that is in the form of 2D and 3D matrices. But in case of 3D representations, for representing an object, we will have different ways of doing that, right? So I have listed those things here, those possible ways here, and let us see them one by one. So one of the way which was used at the early stage of the use of 3D data was in terms of multi-view RGB representation. So here you are basically representing the 3D objects, 3D objects in 3D with the help of 2D images. Now, one thing I'm sure you must have understood that in case of 2D, you have just one pose, and in case of 3D, you have multiple poses. Or you have the information of the object from many directions. So just to have such kind of thing, just by using the 2D images, this multi-view RGB representation was used. So here, actually, we are capturing the object only using the 2D images. But here, in place of just capturing one or two samples, in place of just capturing the object from one or two sides or from 2 or 3 directions, you are actually you are capturing the object from multiple directions, right? For example, you have this object to be captured. So now, in place of just having one or two views, you may be, let's say, going around it and then capturing, let's say, 50, 60 views. So in that sense, you'll see, though the images are 2D, but since you have captured it from many directions, you will be able to get more information about the object. And that way you can say that you have some kind of 3D representation of the object, right? But though, please remember, though in this case, the true representation is in terms of only 2D images. So this is basically a collection of maybe 50, 60 2D images giving you good amount of information about the object. So, and this kind of object representation was used when we did not have these 3D sensors easily available, and it was difficult to capture the 3D data in real sense. Okay. The another representation that we have for the objects to represent them in 3D is by using volumetric representation. Here, this is a true three-dimensional representation, because with the help of this representation, you will be getting the complete geometric information of the of the object. Now here, what we do, so you know that any 3D object is a collection, is a volume basically. So we consider a small unit size cube, and then we try to find out how many. We try to decompose the entire volume of the object in terms of these unit cubes, right? And once that entire volume is divided in terms of these unit cubes, then you represent these cubes with the help of some XYZ coordinate information, and then collectively, if you just assign XYZ information to all cubes, collectively all those cubes can actually represent a 3D object. So here it's called volumetric representation because in this case you are not only representing the outer boundary of the outer surface of the object, you are also representing the interior volume. So this is the second way we can have the representation of an object in 3D. Okay. The next technique that we are going to discuss, and the next way that is used for storing the 3D storing the objects in 3D is in terms of the depth images. So what we do here, so when we capture the image is in terms of 2D image, but here the intensity that you have at every pixel, that intensity is actually telling you about the depth information of the pixel. Right? So it's a 2D image, but every pixel Z value of every pixel, you can say, or the intensity value of every pixel is actually telling you the depth information. So again, in this case also, your representation is not a true 3D representation, because again you are coming back to 2D. But since the intensity values are able to represent the depth, you are saying that this is a 3D representation. Now, there's another representation. Maybe before that, I just go to this representation. It's called the point cloud representation. Here, this is similar to the example I have showed you at the beginning. So here we are assuming that the surface of the object is some collection of some points, and then to represent the object in 3D, we are basically digitizing those points. We are representing those points in terms of XYZ coordinates. So here you see that the object being represented by the collection of those points, where every point is represented using XYZ values. Now, once you have this representation in terms of XYZ, I mean, in terms of these points being represented in terms of XYZ, what next you can do? Actually, you can take neighboring points and then connect them and then create a mesh kind of a structure, where mesh could be like triangular mesh, or maybe using some other kinds of shape. Popularly, we use triangular based, I mean, mesh based on the triangles. So what we do here, so this is a you can say it's a kind of point cloud representation, but a little more rich version, because here the points are not discrete points. Now you are trying to connect them together, and then neighboring points you are trying to connect them, and then you are trying to create a mesh structure where the now points have connection to their neighbors. So this is the fourth way of representing the object in 3D, and point cloud I've already discussed. And then the last one is the primitive based CAD models and representation of any object using them. So what we do here, so you have a 3D object. That 3D object can be considered collection of some primitive shapes, right? So now to represent the complete information about the object, we consider those primitive shapes that are existing in the object, and then we are representing those parts of the object in terms of the primitive shapes that resembles to them. So, for example, let's say you have an object here to be represented. You know that this kind of surface can B-spline surface can fit to it. So you are representing this object with the help of a CAD model, which is being defined with the help of let's say a B-spline surface. Similarly, maybe let's say your object has some planar areas, spherical parts are there in your object. They can be represented by defining the planes and the spheres and so on. Okay? And that way you can have the 3D representation of the object. I'm extremely sorry for this disturbance. Let me just resume. Okay. Yeah, so I was just explaining to you about different ways we use for representing the 3D objects in 3D. And now let's analyze them closely and see can we group them together and then see some similarities between them. So we find that all the 3D representations that we have seen, in all those representations, these three representations, multi-view representation, multi-view RGB representation, volumetric representation, and depth images based representation, all these representations have or all these representations are in some sense a kind of regular rasterized representation where we are using a regular grid. In the first case, these are the 2D images. In this third case, again they are the 2D images. So obviously they are represented in terms of 2D or 3D matrices. And exactly in the same way, if you see this volumetric representation here also, our images are being represented in terms of a grid, right, which is a 3D kind of grid. So in all these three cases, our representation is in terms of regular grid. But if you see the representation that we have here, polygonal mesh-based representation, the point cloud-based representation, or the primitive CAD model-based representation, all these representations are some kind of irregular representation, because here there's no systematic pattern that we are following to represent different parts of the objects. Okay. Now, till now we have seen that there are many ways of representing the 3D objects in 3D. So if you see the literature, there are a lot of now existing literature where deep learning based techniques and maybe some other classical techniques have also been applied on the 3D data. Now, if you just analyze these techniques, you can actually group these techniques based on the kind of data that the technique is using for its analysis. So, if, for example, in some of the works that you see here, they are using the multi-view representation of the data. Similarly, these works use volumetric representation. These are some works here where the point cloud is used, here mesh-based representation is used, and so on. So all these works can be actually classified into different categories based on the kind of data that they are using. Okay. Now we are moving towards the use of deep learning in 3D. So when we talk about, let's say, the use of deep learning in 3D, the common question comes: can we make use of the deep neural network that are available for the 2D data in 3D? For example, CNN is a very popular architecture, very popular deep neural network for analyzing the 2D images. So the question comes: can we make use of the CNN for 3D data? Okay. So understand that whether we will be able to directly use it in 3D data or not. We need to understand how does the CNN works. So in case of CNN, when you are using it, you are performing the convolution operation, and in case of when you are performing the convolution operation, you will be having a matrix, let's say size 3x3 or 5x5, and then you will be convolving your image with the help of that matrix. So to perform this operation, to perform this convolution operation, your image representation should be a very regular kind of representation, and this representation should be actually in terms of the 2D or 3D matrix. Okay, so all the 3D data that we have, all different ways of representing the 3D object in 3D that we have discussed, we'll see that some of them are following the regular representation, and we'll see that there we can directly make use of the CNN, the 2D CNN for the 3D data. But in some of the representations where the structure was not very regular, there we cannot make use of the CNN for those kind of representations, right? So we have seen that in multi-view representation, depth image representation, in the volumetric representation, the representation is in terms of the regular grids, right? 2D or 3D, you can say 2D or 3D matrices. So here, the 2D CNN can be directly applied, and you can make use of them for different tasks. Obviously, there are going to be some challenges that need to be handled when you are going to use 2D CNN in 3D, but it is possible. But when you talk about these representations where the representation is irregular, we cannot directly make use of the CNN there, and we need to look for some other alternative. So we are going to discuss this network. It's called PointNet, and this network is actually useful for implementing deep learning on 3D data when the data is represented in terms of point cloud. Okay, so let us see. Again, skip this. Just to refresh you, we have seen many different types of representations for the 3D objects in 3D. Like one was the point cloud representation, another was the mesh-based representation, the third was the volumetric representation, multi-view representation. These are the different ways that we have just seen, and we'll see that among all this, point cloud is actually very important, right? You have, I mean, if you just consider these four representations, out of these four representations, we see that the point cloud based representation is very important. And the reason is that when you are capturing any object using any sensor, what you first get is the point cloud data. Okay? And later, by adding some processing, you may be generating mesh representation or the volumetric representation or the depth image based representation. So first, when you capture any object using sensor, 3D sensor, what you will be having is the point cloud data. So we are always intended towards developing a deep neural network which can directly consume point cloud data. And if we are able to get that, or if you have something like that, then this conversion can be avoided, right? So, for example, if suppose there is a deep neural network which uses mesh-based representations, so first you have to capture your object in terms of point cloud, and then you have to convert that to the mesh representation, and then then only you can make use of that neural network for this kind of 3D representation, right? So, if you can directly have a representation, if you can directly have a deep neural network which can consume point cloud data, that is going to be really helpful, because this conversion can be avoided. And also one more thing, if you have any deep neural network which can work on the point cloud data, it is very easy to make use of make it work with the other kind of representation, because conversion from these representations to point cloud is very simple, very easy. Going from this to this is difficult. Going from point cloud to the mesh or volumetric representation or the depth image representation is difficult, but converting these representations, volumetric representation or the depth image representation or the mesh representation, converting these representations to point cloud is very simple. So even though your data is represented in terms of these representations, you can easily convert that representation to point cloud and then make use of your network. So just to summarize, if you have a deep neural network which can directly consume point cloud data, you can obviously it can work with the point cloud data, but at the same time it can also be customized to work with the other representations, because those representations can be easily converted to point cloud data. So our idea here is to have a network which can directly directly consume point cloud data, and we'll see that the network that I mentioned, the PointNet deep neural network, that actually directly capable of consuming the point cloud data. So let me just skip this and then directly go there, because I think the time that we have is less. Okay. So let us discuss the PointNet. So what PointNet does, as I just said, it can directly work with the point cloud. So if you have this PointNet network, this can directly consume the point cloud data, and by analyzing the point cloud data, it can perform different types of tasks, like object classification, object part segmentation, semantic scene passing. Lot of things it can do. So that's why I say that this is a unified framework for the various tasks. Okay? And as I said, it can consume scattered unordered point cloud data. Okay? And yeah, so these are different types of tasks that it performs. So for example, classification, where the object is being represented in 3D and then it it is able to classify them in different categories. Similarly, even for a single object, it is able to classify different parts, and also it can, it can it can parse different parts of the captured data, and then also associate some kind of semantic to it and perform the semantic segmentation. So PointNet is found to be quite powerful network, which can directly build the point cloud data and then perform many important and useful tasks. Okay. So now let us understand what is the challenge when you are dealing with the point cloud data, and how does it being handled in case of deep neural network. So you know that point cloud data is an unordered data. If you when you are representing an object with the help of collection of XYZ coordinates of different points, there is no order in which you are actually bound to place these points in your representation. So say that, let's say if any object is being represented using n points, you can have n factorial different ways of representing it. N factorial ways are basically putting it in your representation, and all of them will be actually representing the same thing. Okay, so one challenge that comes when you are dealing with the point cloud data is because of its unorderedness, and second is it imposes some challenges because you will see that it will be the representation will be dependent on the kind of geometry, the kind of view that you are using to capture it, right? For example, so what I'm saying here is that the 3D data will be you will be representing the object in terms of complete geometric information, but the coordinates, the values of the coordinates that you are going to use to represent different points that are lying on the surface of the object, that those coordinates may be different based on different uh, starting view that you are using for capturing the data. So I think this point will be more clear when we go ahead. So let us first understand what is the meaning of, or what is the challenge we face when we have this unordered data. So when you are saying that this point cloud data is unordered data, or it doesn't have any order, we are basically saying that, let's say you have n points being used to represent your object, and those endpoints are being represented in d dimensions. So if you put those points, let's say in this order, or let's say you change the order and then you put them in this order, both of these things will be representing the same object. Right? For example, here the blue point, the blue part is first, the blue part is last here. So that means the point that you are keeping here as the first point has become the last point here. Similarly, this is the second point here. This has become the first point here. So though you have changed the order in the points, but still collectively these points here are representing the same thing. Just to see this more precisely, let us just understand it with the help of this example. So let's say you have a 3D face here, and you have digitized, you have represented this 3D face with the help of 3D representations, where you are assuming some points on the surface and then you are digitizing them in terms of XYZ coordinates. So effectively you get these, let's say, set of points to represent this object, right? So let's say there are 10,000 points here which are being used to represent this 3D face. So in this file, you have all those 10,000 points being listed, and for every point you have 3 values which are representing the XYZ coordinate of that particular point, right? Now, let's say this is a text file where you have kept all those XYZ coordinates of all the points. Now, if you open in the software, you will see that the software will show you this face, right? Now, what you do, let's say you take the first 10 points of this file, first 10 points, and then you keep them at the end of the file. So in the new file, this point becomes the first point. Okay, and all these 10 points are being kept at the end of this file. Now, if you open that this file too with the help of your, let's say, software which is capable of showing this 3D data, again you will see that it will be showing you the same object, because just by changing the order of the points, the representation doesn't change. Okay? And this is what we say that if you have n points in your representation, you can actually have n factorial ways of representing the object the same object. And this is actually a challenge. And this is a challenge because if you compare this with the representation that you have in 2D, in 2D you have a very unique representation. So for example, let's say you have a 2D image like this, right? If you change the order, and let's say you consider that the image is having 4 parts. Now, if you, let's say, swap this part with this part, you can easily say that the image is not going to be same. It will be a different image. But here you see that even when you have changed the order in these points and you have created a new file, the file is still representing the same thing. So let's say in case of 2D, you have swapped these 2 parts and you are applying the CNN. Your network is not expected to behave in the same manner. When let's say you have trained the network with this image, and then while testing you are supplying the image where these 2 parts are swapped, you are not expecting that your network should actually recognize that image. But here in this case, you are expecting that in both these cases, the network should be able to recognize that this is representing this particular object, right? So let us see how it is handled when you are dealing with the when you are doing this with the help of pointed. So pointed is basically making use of a symmetric function for overcoming this permutation problem. So what it does, so it makes use of a symmetric function. So first understand what is a symmetric function, and then we'll see how it is being used in pointed. So let us take this example. For example, max is a symmetric function. So in a symmetric function, when you are passing the parameters, the output of that function doesn't depend on the order in which you are passing the parameters. So for example, here, let's say you want to find out the maximum of these points, x1, x2, x3, xn. You have n points or n values, and you want to find out the maximum. If your function is max function, it doesn't matter whether you have passed x1 to it first or x2 to it first, or in whatever order you pass these x1, x2, x3, xn values to the max, you will be getting the same output. So here, max function can be considered a symmetric function because the output of this function doesn't depend on the order in which you have supplied this point. Similarly, another example could be the sum function. So here, when you are summing n values, in whatever order you are placing them, the final output is going to be same. Okay? So this network, this point net, actually makes use of makes use of a symmetric function, and particularly it makes use of max function actually to handle this permutation problem. So what it does, it doesn't consider the as I said, it is going to consider the point cloud data. So in case of, let's say you are supplying the point cloud data in terms of capital N points. So it is not going to consume that data in terms of those capital N points. From that, with the help of symmetric function, it is going to generate some alternate representation, and it is going to make use of that representation. So since that representation is being generated with the help of the symmetric function, you know, the output of symmetric function doesn't matter in which in the order input is supplied. So in whatever order you supply your point cloud, the final representation that it is going to use will be always same. So we'll see that. So effectively, this network does this operation. So x1, x2, x3, these are going to be the input to the network. It is going to perform some kind of operation on these individual outputs, individual inputs, and then over those obtained values, it is going to perform this operation called G, which is going to be a symmetric operation. So, and then whatever output is coming from here, it is going to combine with this, and then finally it is going to produce the output. So pictorially, if you see how does this network work? So here, your input to this network is going to be point cloud data. As I said, this network can directly consume the point cloud data. So point cloud data you are going to feed to this network. So so different points are being represented in terms of some XYZ values. So those values are being fed here. Now it does some kind of transformation on these values. So it applies this function S on them, and then whatever output you are getting after applying this function S on that, it is performing a G operation, which is a symmetric function, and it is actually using max function here. And then this output, this representation that you get here, is being fed to the neural network, which is going to perform the classification. So you see here that in terms of input, you have the point cloud data, but after using this G function, which is a symmetric function on this data, you are getting an alternate representation here. Now, this alternate representation is obtained with the help of symmetric function. So this representation is invariant to the way you are supplying these points to this network, and that way it is actually able to it is easily able to handle the permutation problem of point cloud representation. Okay, let us understand what how you are able to do that here. So before that, let me tell you. So what actually it does here, H, the role of this H is to project this three-dimensional data to the higher dimensional space. So as I said here, that you are going to use a max function. Now, if you're directly using the max function on these values, let's say you are computing the max of each coordinate, then when you are performing the max on these values, you will be getting some three values, right? One value for each coordinate. And now, if with the help of this three value, if you are thinking of representing a big object, it is not possible. So this network actually performs the symmetric function, but at the same time, it is also able to retain the actual information that is being supplied in terms of these XY points. So let us see how does it do. So to retain this information, the network directly does not perform the max operation or the symmetric operation on this original data. It actually projects it to the higher dimensional space, and then it performs there. And we'll see that because of this projection, you will be able to retain the information up to quite extent. So what it does actually, it takes the three-dimensional data and it projects it to high-dimensional space. So here I'm just for the demonstration, I'm considering that high-dimensional space is 12-dimensional space. So you are projecting this 1, 2, 3 to 12-dimensional space, and let us say you get this. Similarly, you are projecting this also to 12-dimensional space, and you get this. And this is also projected. This is also projected in that 12-dimensional space, and you are getting this. Now you are performing the max operation. So now when you are performing the max operation, you are getting a 12-dimensional vector here. Now you see that in this 12-dimensional vector, you have the representation for the first point, for the second point, for the third point, and also for the fourth point, right? So even though you are considering just one vector now, it is actually having some representation from all these 4 points that you have considered here. So when you are actually taking your points, 3D points to higher dimensional space, many of the values will be 0, and there will be only very few non-zero values. So when you are computing the max, it is it is possible that you will be able to retain your non-zero values that are coming from your original data. Okay. In this synthetic example, you see that all those 4 values are being represented here in this 12-dimensional vector. But in general, when you are dealing with a real case, you may not be able to do that. But when you are projecting this to very, very high dimensional space, it is very much possible. And we'll see that in the case of PointNet, this projection spaces, projected spaces in 1024 dimensional, in 1024 dimensions. So it's highly likely that you will be able to retain the information. I'm just skipping this in the interest of time. For this H network, this network is using MLP, multilinear perceptron, and as I said, for G, which is a symmetric function, it is using max, and then again for the classification also it is using max. Let me just now quickly tell you the way it is handled. It is able to handle the or it is able to create the invariance in the 3D data. And I think I'm already running out of time. I will be just taking maybe 5 to 10 minutes to conclude my session. So I hope that should be okay. Okay, so let us see how does this network handle the geometric transformations. So let me just quickly tell you what this problem is. So let's say your object is something like this. Let's say, and you are, let's say your XY, the frame that you are using to represent this is like this. So when you are representing the X coordinate, the XY, you're computing the XY values for different points that are lying on this object. Let's consider first, let's say you're trying to find out what is the X coordinate for this point. So with respect to this origin, let's say, I mean, I'm just taking a 2D case. With respect to this origin, you will be having some coordinate value for this. But now let us say this object, when you're when you are capturing it, it is not in this orientation. It is little tilted. Let's say it is like this, right? So that means this point has come somewhere here. Let's say. So object is same, but the point has come here. So now if you are with respect to 0, 0, if you are considering this point, it will have different xy values. Okay. So though the xy
We
values,
kindly
collection of
request
xy values
everybody
that you
to
are going to get
maintain
from here,
silence and make use of
or
this
the collection
session.
of xy values that you are going to get from here, both of them are going to represent the same object, but those values will be very different. Okay? So because of these geometric transformations, you see that the entire file that you get for representing your object changes. So how to handle that? Because here, if this is the view that you have taken, sorry, or in this orientation, let's say if you have captured the object, you will be having different set of xy values. If you have captured this in this orientation, you will have different set of xy values. So how to handle this? Because if the xy values are different, then obviously your network is going to treat them in a different way. So to handle that, this network suggests automatic alignment of the object. So what it does, uh, whenever the object representation comes to it, it doesn't consider that representation directly. First, what it does, it actually aligns the object into some standard axis, and then only consider it for the further processing. So how does it help? Let us see that. So for example, let's say your object is in this orientation, and in another case, the object is having this orientation. Now, before considering these two cases, if you, let's say, align this data in such a way that, let's say, this axis in which the data distribution for this object is high gets aligned to the x-axis. So this will be oriented, and then it will be oriented like this. Similarly, if you do the same thing for this in its oriented representation, this will be also again will be represented in the same orientation, because after getting the data, you are orienting it in such a way that it's the axis in which the data distribution is high becomes, let's say, parallel to x-axis. So in both the cases, whether the data is given input in this format or in this format or in this orientation or in this orientation, in both the cases, first you are going to align that to this to some automatic so to some standard axis. So this will be effectively going to give you the same view, and then that will give you the same kind of xy points for the same xy coordinates for different points. Okay? So the geometric transformations are actually handled here with the help of this kind of automatic alignment. Now, when you are doing the automatic alignment, you need to have the parameters that are going to perform this alignment. So for that, there's a T network which is used here. So it takes the input point cloud and does some processing, and then can compute the transformation parameters, and based on those transformation parameters, the data is actually being transformed, and this transformed data is only used for the further processing. So here, if you see more closely about the processing that is being done here, the TNet gives you the transformation parameter, which are going to be in terms of 3x3 matrix, and then that matrix is going to be multiplied with this original data, and you will get the transform data. Now, this transform data will be able to align the data to some standard direction, and by that way, whatever orientation you have in your input case, the transform data is going to be always aligned to some standard axis or to some standard direction, and that way the problem of geometric transformation will be handled. Okay. In this network, we'll see that this kind of alignment is done at two stages. One with the original data, and another with the data when it is of size 64 plus 64. So we'll see that in detail in the complete diagram of the point net. Yeah, so that's here. So let us understand the complete pipeline of the point net network. So input to this network is going to be the point cloud data, and then on this point cloud data, you are going to perform this transformation to align it to to the standard direction. So you are using the TNet here for this alignment, and after this you are getting a three-dimensional, the data being represented in 3 dimensions, and that is now aligned. Now for this aligned data you are using the projection. So this 3-dimensional data is now projected to 64-dimensional space. You remember I said that to handle the unorderedness in the point cloud, you are going to use the symmetric function, and that symmetric operation is is going to be performed in the projected space, which is going to be of 1024 dimensions. So here we are trying to take this data which is in 3 dimensions to 1024 dimensional space. Now this projection is not a one-step process. It is actually done in 2 steps. First, the 3-dimensional data is projected to 64-dimensional space, and then the 64-dimensional data is projected to 1024-dimensional space. So from here to here, we have projected the data from 3 dimensions to 64 dimensions. Now this 64-dimensional data need to be projected to 1024-dimensional space. But before that, it again performs the alignment. So similar kind of alignment that you perform on the 3-dimensional data here, the same kind of alignment is being performed on the 64-dimensional data, and we get the aligned data here, and then now this is projected to the 1024 dimensional space. So finally, we get data which is in terms of 1024 dimensions. Initially, the data was in 3 dimensions, and now the data is in terms of 1024 dimensions. So you have number of points are same. You have endpoints here, you have endpoints here, but now the number of dimensions that you are using to represent a point have changed. Here you are using 1024 values or 1024 dimensions to represent a point. Here you are just using 3 dimensions to represent the point. So now the data has been projected from 1024 dimensional space to 3-dimensional space. From 3-dimensional space to 1024 dimensional space. So now the network actually uses the symmetric operation on this data and gets this global representation, which is again a vector of size 1024. And for as a symmetric function, it is using max operation. So in terms of your deep neural network language, you can say this kind of max pooling that you're doing here. And then what in the classification network, and the classification is being performed. Okay, and so here if you analyze this complete pipeline, you can see that you are getting some sort of features here and some sort of features here. Here for complete object you are just having one vector, so you can see this kind of global representation for the object, and here in this case for the object you have I mean, these are features, but again, you have number of points same. So you can say that these features are kind of local features, and here you have the global feature. So if you combine these global and local features, actually you can have a good representation for different parts of the object that you have in your object. So by using such kind of embedding, actually the point net is able to perform part segmentation. So if you're just using this pipeline, this does the classification, and if you just do if you combine the local embedding and this global feature and then use those features for the classification, it is able to perform the part segmentation. Right? So let me just quickly show you the results. If you compare the performance of the point net with the other existing networks which were using the 3D data, you see that this performance is at par with those existing networks. Now, though the performance is same, we are happy because in other 2 examples we were using the we are using the volumetric representation of the data, which is bulky and then takes more time. But if you are able to achieve the same result using the point net, since it uses only the point cloud data, which is the surface information, in terms of time, it is quite fast. These are some visuals for the part segmentation. I think I can just skip this. These are few results for the semantic scene parsing. So you see, you are for these inputs, you are able to perform different parts, and also you are able to segment different parts, and also at the same time you are also able to label them that this is chair, or this is a roof or things like that, table, wall, and things like that. Okay, so different parts you are able to associate semantics with the different parts. I think I'm completely out of time, so let me just quickly summarize my talk. And I can
Silence.
skip all this. Let me just conclude it by saying that we have discussed here a network which is called PointNet, and it's a deep neural network which is a very powerful network, and it can be directly used with the point cloud data. And it is a very powerful network in the sense that it can perform many different types of tasks using just just a similar network. For example, the same network is capable of performing classification. The same network can be customized and used for the part segmentation, even for the semantic scene parsing. So many different types of tasks can be actually performed with the help of just this one network, this PointNet. From the author's website, if you're interested to use this network, you can go to this link and then get the code and the data for this network for the PointNet and make use of for your problem. And the main reference that I've used for this presentation is this paper, which was published in CBPR. And I've also borrowed some of the slides from the author's presentation. So I just want to give credit to them. And with this, I would like to conclude my session. I'm really sorry for the disturbances that came along. I hope I was able to convey something. If there are any questions, I will be really happy to take them.
Thank you, sir.
Yeah, thank you. It was a pleasure.
Thank you, sir, for instilling an immense knowledge towards the participants.
Sir, thank you so much, sir, for the
Thank you.
thank you so much, sir. Thank you, sir. Thank you, sir.
Hello.